formed by tectonics. And then the landscape, the orography is affecting the climate, causes precipitation, different temperatures, and so forth, and that affects erosion. And erosion, by removing mass, by removing material, is also feeding back into tectonics, but also into climate on a larger scale. And whoops, there you go. And there are a couple of either large or small scale processes, some of them highlighted here, like when a mountain range is forming an orographic barrier, which influences atmospheric circulation and orographic rainfall, but also focusing, especially in areas with the monsoon precipitation, can lead to focused mass removal and therefore feedbacks into tectonics. At the same time, climate change periods, like quaternary glacial cycles, can affect the way the mountain range is eroding in different places, which again has an influence in tectonics or even back into climate when it comes to the global current cycle. So there are many different aspects of different scale in time and space that make this triplet of climate, erosion, tectonics, and the interactions very interesting. And this is especially true for the Himalayas. Why? Because it is a very wet place. And this figure here, I think, is from Kolkata, somewhere, I think, to me, always embodies the monsoon season when tons of rainfall are pouring down on the landscape. And this map up here from Bodo Borghagen and Dirk Burbank from quite some time ago shows rainfall as depicted by the Tropical Rainfall Measuring Mission, and highlights these high rainfall bands that are occurring over the Himalayas. The first one at lower elevations, and the next band here at higher elevations in the Himalaya. And this particular coincidence of high precipitation at the front of the Himalaya has long been a starting point for many researchers to delve into questions how tectonics here and surface denudation induced by monsoon precipitation may be linked. And this goes back in time. A study by Peter Clift and others suggested that Himalayan exhumation rates over long time scales is linked to Asian monsoon intensity. There were other people suggesting that there is some sort of decoupling of erosion and precipitation, possibly induced by quaternary glaciation. Other about the long effects of organic carbon burial in the Bay of Bengal induced by Himalayan erosion and what that means for the global climate. And then there are a bunch of other studies that consider more generally the links between climate and erosion over longer timescales. And in these questions, the Himalaya always plays an important role. Now, starting from these questions, there are a couple of, or these topics, there are a couple of science questions that we can come up with. And they are most basic, relatively fundamental, and they include topics such as what controls the magnitude and distribution of erosion in a mountain belt like the Himalaya. Second, erosion rates. Do they vary along with climatic changes? And if so, by how much? And is it really all about precipitation, as these previous studies might suggest? So that when precipitation in the past goes down, do erosion rates go down, or is it different? And how stable or variable are erosion rates in the long term? Does climate and climatic changes really matter, or is the most important thing actually the tectonic forcing that is building a mountain range, and therefore climatic changes are more ornamental in the long term? Other questions consider also things like glaciers, because during the Quaternary, we know the glaciers have been very important and effective landscape agents. And how have they affected the evolution of landscape in the Himalaya? And how, now coming towards the present day, how does the current climate change affect these landscapes? So a couple of questions that all are centered somehow around erosion and how it's spatially and temporally distributed. So in the following now, I first want to give a brief introduction to Cosmogenic Nuclides, a tool that we use in order to quantify erosion rates, but not only. And then I want to address or provide some examples from the Northwestern Himalaya, as shown here, that all are using cosmogenic nuclides, and in which I have been involved, or the driving force of these studies. And so there are 6, I think, I provide here, but I don't have to go through all of them. If things become unclear or you have questions, please interrupt me. And if then time is to, when I'm taking too much time, then we could also easily stop earlier. So I'm awaiting your feedback. Basically, if you say, look, I have a question here and there, and then we can also start discussing things. Okay, so let's, good terminology. When talking about erosion, this is a term that also in the public is relatively fuzzy. And in science, we mean with erosion really the removal of material from the Earth's surface by physical processes. Whereas chemical dissolution, this is what we term weathering. So dissolution of minerals, for instance. And when we say erosion and weathering, when we mean both together, then we say denudation. But in everyday language or everyday discussions, we sometimes are not paying a lot of attention to these distinctions. And therefore, I also use erosion and denudation quite often synonymously. So when I say erosion in the following, let's say 40 minutes or so, I sometimes mean denudation with it. But if I specifically say weathering, then I mean weathering. So excuse me if there is a little bit of uncertainty along those lines, but I try to be at least honest about it. Okay, so cosmogenic nuclides. We start here with a new supernova. This is a new one because it's based on a galactic image or something where it has been spotted. But generally speaking, supernova are the main source of galactic rays. And supernovas are explosions of stars. So it's really when a star like our sun is exploding and sending particles in all directions with enormous kinetic energy. And these events happen all over the universe and throughout the entire lifespan of the universe. And they are the sources of galactic cosmic rays. So these high energy, high kinetic energy primary particles that come from supernovae are hitting our atmosphere, and they are creating a shower of secondary cosmic rays, a cascade of secondary cosmic rays that eventually trickles all the way down to the Earth's surface, where it interacts with minerals. I don't want to go into the details of all these cosmic rays because it becomes quite complicated. But the primary cosmic rays are protons, so helium cores, and in the atmosphere they interact with the molecules such as nitrogen or oxygen. And then the secondary cosmic rays, they have a couple of different particles, but the most important ones are neutrons that interact with atomic nuclei in surface minerals, where then spallation processes are creating cosmogenic nuclides. So here's a figure that considers a proton that is coming down through the atmosphere, interacting with an oxygen molecule. And even in the atmosphere, we're producing cosmogenic nuclides. So for instance, meteoric 10 beryllium is produced. But the more commonly known cosmogenic nuclide that is produced in the atmosphere is obviously radiocarbon, so C14, which is eventually then incorporated by plants or animals when they are growing and living, and which we use for dating these organic remnants using radiocarbon dating. But in principle, it's a cosmogenic nuclide. And then a neutron is traveling further down through the atmosphere and interacting with minerals at the Earth's surface, for instance, oxygen within quartz, and is producing another cosmogenic nuclide. Here also depicted as an example is helium. Even 14C is produced within quartz minerals. So there are a variety of different cosmogenic nuclides, but the main emphasis in this talk will be on in situ produced 10 beryllium. The key principle for using cosmogenic nuclides as stopwatches of the Earth's surface is the fact that the production rate of cosmogenic nuclides, such as 10 beryllium, is decreasing with depth into the ground. So at the surface itself, the production rate is at maximum, but then due to the interaction of these neutrons with materials, the production rate decreases exponentially with depth. And at a depth of a couple of meters, production rate is essentially negligible. So it's really something that occurs just at the skin of the Earth's surface. And there, the production of cosmogenic nuclides provides a tool for us to date surfaces or quantify erosion rates. We usually do that with not all the cosmogenic nuclides that are produced, but with a handful where the knowledge about production rate, half-life, and so forth allows us to use it, to exploit the system. So here are a couple of nuclides listed in this list. There are 2 stable ones that are commonly used, and this is 3 helium and 21 neon, so noble gases that are stable. Then there is also 14C that can also be produced within quartz. The half-life is the same half-life as 14C produced in the atmosphere, obviously. And then there are nuclides such as 10 beryllium, 26 aluminum, and 36 chlorine. 10 beryllium is by far the cosmogenic nuclide that is used the most because it is very well characterized. It is easy to extract, or relatively easy, let's say. And it occurs in quartz where it's retained quantitatively. So whatever 10 beryllium is produced in a quartz grain is not diffusively lost, but it stays in there. This is not true, for instance, for 3 helium, which can also be produced within quartz, but it diffuses out of the crystal lattice. So 3 helium in quartz is not so useful, whereas 10 beryllium is very useful. 26 aluminum can also be measured in quartz. It has a higher production rate. Note the low production rate here of 10 beryllium and a lower half-life. So these differences in half-life can also be exploited for certain applications, but I'm not going to go into too much detail of that. Chlorine 36 is useful because it can be quantified in calcite. And so this nuclide is predominantly used when working with limestones or generally carbonate minerals. Okay, so we'll be focusing on 10 beryllium. Now, the 2 applications I mentioned is exposure age and denudation rate. And here I'm showing the equations that we use in order to calculate an exposure rate or a denudation rate, neglecting radioactive decay. This need not be neglected. We can set up equations that include radioactive decay, but for simplicity, I just avoided it here. And it's quite simple. All we need to do is to measure the concentration of a cosmogenic nuclide and to know the production rate. The same applies here. Measure the concentration and know the production rate. The rock density is a constant that we can infer or measure, and the attenuation length is a constant that we know. So relatively simple a tool to where we measure something, know something, and then obtain an exposure rate or denudation rate. How do we do this? Well, we go to the field. Here's a field photograph from the Barashigi Glacier, and just before it turns around the corner and enters into the Chandra River, there is a bedrock knob. So it's basically a hill, a couple hundred meters above the glacier. If you hike up there, you will see striated surfaces and some boulders and erratics lying around. And so here we went in order to collect samples for exposure dating of these boulders up high on this bedrock ridge. So taking the samples to the lab, we then need to process them, typically in a clean lab, because the quantities we want to measure are very, very low. And because they are so low, so we're talking about concentrations of let's say, tens of thousands to hundreds of thousands atoms per gram. And because atoms per gram are really low concentrations, in order to measure that, we need to use an accelerator mass spectrometry. Here is an instrument such as the one that stands at the University of Cologne, where we send most of our samples to, and it measures several tens of meters in size. And the way this works for this accelerator mass spectrometry is that you have a sample that is accelerated, and then here is a gas chamber where some nuclides or some elements that are not wanted are stripped off, and then magnets in this part here are forcing the beam of particles to turn around, and then by mass that splits up. So the heavier atoms are farther outboard, the lighter atoms are farther inboard, and then at the end here there is a target where the different atoms are counted as they enter these different chambers. So this is the way that we quantify the concentrations. But in fact, the concentrations are not directly measured. What we are measuring are ratios. So we are measuring a ratio between one nuclide towards another. For 10 beryllium, we always measure 9 beryllium relative to 10 beryllium, or 10 beryllium relative to 9 beryllium. And the abundances of 9 beryllium is about 10 to the 14 times higher than 10 beryllium. So it's really tiny quantities that we try to measure. And therefore we need an accelerator. Okay, so exposure ages, I mentioned this. The line here so here you see the duration of exposure to cosmic rays. This is the concentration. We measure a concentration. We know the production rate, which is the slope of this line, and then we can infer the exposure to cosmic rays, so the exposure age. For denudation rates, it's a little bit different. The concept is that minerals at depth are slowly migrating towards the surface because the surface is eroding. So it's in a relative ascent of a piece of rock, let's say. And as it ascends towards the surface, it passes through this zone where cosmogenic nuclide production occurs. And because production is high at the top and low at the bottom, the concentration of a particle of rock or of quartz mineral is slowly increasing. And it not only depends on where it is located in this at depth, but it also depends on the erosion rate. Because if the erosion rate is high, the ascent of the particle or of the rock is fast. And therefore, at the end of the day, when it arrives at the surface, the concentration is low. Whereas if the erosion rate is low, then this ascent is very, very slow. And during this ascent, there will be a lot of production of cosmogenic nuclides such that the concentration at the end of the day is high. And so these differences in concentration translate into differences of denudation rate. This is an example of one particle of rock or one mineral, if you want, that ascends towards the surface. This may occur just outside of your institute, but it occurs all over a catchment. So let's assume here is whatever it is, the Giri River or so, and that drains a larger area, and somewhere up here is maybe Shimla. But the grains of quartz that are exiting this river and then are flowing into the Yamuna or so, they come from all over the place. So these quartz grains, all of them have an individual history such as this, and they carry the information in terms of the concentration with them. And if you collect a sample of sand from the river here and measure the average concentration in all of these sand grains, then you get an average concentration that corresponds to the entire catchment. And so this is one particular way that has been employed many, many times in the last 20 years or so in order to estimate. Yes, please.
Sir, climate do any affect to the denudation rate?
Sorry, can you repeat the question? I didn't get it.
Sir, is climate to any effect to denudation rate?
Climate, potentially yes, but we will come to this question a little later. Climate, if it affects denudation rates, then it would yield a different concentration. But climate is not the only factor that influences denudation rates. There are other factors that influence this. And this is what we can try to tease out of the landscape and of our samples when we collect samples such as this one.
Okay, sir.
Okay?
Yes, sir.
Sure. Thanks for asking. So when we collect our samples here, we get a catchment average denudation rate for this landscape. Also, because sediments are sometimes deposited in river valleys, and this is supposed to reflect a valley fill that might be exposed once the river incises again, such as the river terrace that you might see down in the Paba River or in the Tons River or wherever. Then you can collect samples from these terraces and infer that this material has been deposited by this river in the past, and that you then obtain an idea about the denudation rate in the past when the sediment has been deposited. So quite powerful in order to reconstruct denudation rates through the past. Now, one thing I didn't mention so far is the time, the time scale of denudation rate. Because as the rock approaches the surface and produces cosmogenic nuclides, this takes time. And typically, we are saying that the time scale over which these denudation rates are obtained correspond approximately to, or they are related to the erosion rate. If the erosion rate is something of the order of 1 millimeter a year, then the time scale is approximately 600 years, about 1,000 years. If the time scale is only, if the erosion rate is only 0.1 millimeter per year, so it's a lower denudation rate, then the concentration that is in the mineral is acquired over a longer time period. So then the time scale over which these denudation rates average are more on the order of 10,000 years. Whereas if it's faster, then it's shorter. But as an average, you could say that for denudation rates that we observe in the Himalayas, you can see the time scale that these denudation rates provide us, that the time scales that we approach with these cosmogenic nuclide-derived denudation rates are on the order of 1,000 to 10,000 years. And this is advantageous because it is averaging over many different erosion events. It is somehow also averaging over the impact of humans on the landscape and provides us something like a background denudation rate. Okay, so how does it look like when we consider this concept in the landscape, just to make sure that we all understand how this works? Here, this is a view from the Spiti River. Back there, I think that and here is a schematic slice through the landscape, and that I envision. And now the rays are hitting the surfaces here all over the place, and the concentration is high in some places and low in other places. The deep surface here is at great depth and out of reach of cosmic rays, and therefore the concentration is low, 0. But as we get closer to the surface, the concentration increases because their production occurs. The hill slopes records the denudation rate on these slopes. And if the regolith is creeping into the river, and then the river is transporting the material, the present-day river, as well as the material that has been deposited by the river here, records the denudation rate of the entire carrier upstream, or the paleodenudation rate when we go back in time, as we do if we drill into the valley fill here. Secondly, we see there is a fill terrace here, and this terrace has been created with material that was deposited, and then the river has been observing material here that comes from upstream, and some of it is coming from the tributary valley. This is why I sketched this zigzag pattern here with a lower concentration, because I know that in the valley here, I think there are a couple of glaciers in these valleys, and they tend to erode quickly and transport material that comes from underneath the ice, which has a low concentration because it is covered by ice, right? So this is why there is a low concentration here. But the surface is a stable. You see, it's totally flat, and any flat surface is very difficult to erode. It occurs from the sides, as we can see here. So the river is hitting this terrace, and gradually it's eroding. Right on the, it's flat, it's not eroding. And therefore, the terrace surface can be is a stable feature that accumulates. So we can date the terrace surface, the okay, so these are some examples of how we can apply cosmogenic nuclides in a landscape such as this one. And we're going to go towards some real landscapes. We did and a bit into some of this. Everything clear so far? Are there any questions?
Right, so we are clear with the methodology. You can proceed further.
Okay, thanks. Okay, so you're all familiar with this place. I think Shimla is somewhere here, right? Or there, I'm not entirely sure. And this is the Paba River, the Tons, the Yamuna, and no, sorry. This is the Yamuna, and this is the Bhagirathi, I think, right? And these are the sites that we will address in the following. And then also some sites up here from the Chandra River, from the and a little bit from the Spiti Valley up here. Now, these are all studies that I've been working on during the last 10 to 20 years. The most recent studies published with a colleague of mine, Sanjay Kumar Mandal. He's now a professor at the IISER in Kolkata. But I don't want to go into the details of those studies because that's really becoming rather complicated when we're looking into foreland basin deposits, because these deposits have a complex history of exposure to cosmic rays, and it would take too much time to go into this. But for the other ones, I think I can start off with some glacial landscapes up here, even a little glacier that we looked at, and then go into fluvial landscapes and try to demonstrate how we use cosmogenic in order to understand these the landscape evolution in these sites. I don't want to go into too much detail of any of the study, but basically focus on the application and what we can learn from that. In case you're interested, I also gave a presentation on eroding the Garhwal Himalaya and the question of climatic versus tectonic controls on erosion in this Landscapes Live seminar series. It is something that is featured on YouTube. It's an EGU initiative, and there are many other interesting talks, and there are frequently updated new talks coming to it. So I really recommend this to you in order to dig deeper into geomorphology, questions related to geomorphology in general. So really useful resource for you to maybe spend some time other than lectures. Good. So coming back to our studies, first the one here from the Tons Valley. This is a study that the first one that I conducted during my PhD thesis. So we went into the Upper Tons Valley and collected samples from moraines. So basically from lateral frontal moraines where the glacier had been and deposited material. And some of these rocks on these moraines are relatively big boulders, pretty stable. And so we climbed these boulders and collected chips of rocks that we then took to the lab for exposure age determination. Why? Because glacial advances and retreats tells us something about climate changes in the past. And this is interesting because glaciers are a major control of sediment production during glacial times. And so the glacial advances and retreats tell us something during which times have glaciers been bigger, during which times could they have been producing more glacial material that is then transported downstream into the fluvial landscape where the rivers have somehow to cope with this sediment. So we will get to the fluvial landscapes downstream a little later, but first have a look at these glacial oscillations. So all of these DS symbols here indicate samples that we collected. This here is Harkidon. I don't know who has been there, but it's a very pretty area. also with a little hut where you can then start hiking up to the Jaunda Glacier or other glaciers up here. The Banda Punch Glacier in this valley is also very pretty, and there is a little hut in Rinsara Tal where you also see very pretty and beautiful moraines. Some of the moraines are shown here. This is remnant of a lateral moraine in the, down here in the Tons Valley. This is one around the corner. This is up here, it goes to Rinsara. And then this is Rinsara Tal with the other beautiful lateral moraines that can be seen here. Further ones up here, this is Harkidon, and there is already the glacier seen with the more recent, probably Little Ice Age moraines. Now, from all of these moraines, we obtained samples, took them back to the lab and dated them with cosmogenic nuclides with 10 beryllium explicitly, and then synthesized this into this little figure where we can see that the moraines closest to the present day glacier have ages of something like 0.4 to 0.8 kiloyears, so 400 to 800 years here, 200 to 300 years there. But you also see that the uncertainties here are relatively high compared to the age. So in general, you can say the ages of these moraines are relatively young. What exactly is more difficult to say. When we go to older moraines, such as those ones here, they are at 4.7, 5.3, and 5.5 kiloyears, whereas those ones here are at 8.1, 8.5, and there is another one at 8.5. These are from the middle and early Holocene, and there the uncertainty is still on the order of 10% or something back then, but nevertheless, it gets us a better handle on the chronology of these moraines in the past. Farther down here at the junction, we see moraines that are on the order of 12,000 years, and then the oldest moraine farthest down the valley has an age of around 14 to 16,000 years. So what do we see? We see, first of all, there's a clear progression of younger towards older moraines, as we would expect. Then we see that the spread of ages gets relatively large as we go towards the highest ages. So this is also depicted here. Time is on the x-axis, and the ages here are spread out more pronounced than they are towards the younger moraines. And this is expected because moraines are a pile of sediment. And when you expose a pile of sediment for 15,000 years to monsoonal rains, it clearly gets eroded and modified. And therefore, the ages that we obtain from old landforms that are exposed to rain and weathering and everything is always taken with a grain of salt, because these ages might be too young relative to the actual age of the moraine. Okay, other than that, we see a couple of events, let's say, or times when glaciers have receded. So this is what we're dating, right? We're dating the construction of the moraines, and typically when the glacier is receding from these moraines, this is when the clock starts ticking. And compared to places that have also glacial chronologies, like the Gangotri area, here higher up in Lahul, or even Nanga Parbat area in the far west, we see there are some commonalities, but also some differences. And I don't want to go into too many details here, but one thing that we found interesting is that we see this early Holocene advance, which people have been interpreting to be related to enhanced monsoon precipitation during this time. Because from a temperature point of view, it got generally warm during the season. So there's no reason why there should be something like an advance, a re-advance of the glacier during this time period here. But if there was an increase in precipitation relative to previous times, that might be the reason for this glacial advance. And this has been seen not only in these places nearby, but also in other places along the Himalaya. With these older advances, it becomes a little bit more tricky. There's much more scatter, and I'm not up to date with the most recent literature on chronologies from the Himalaya, but I know that there is some discussion about whether certain events in the climate history or things like the Younger Dryas have been relevant for for glacial advances in the Himalaya, which is not entirely clear because it's quite far away from the forcing, from the driving mechanisms. Like the Younger Dryas here and Heinrich events are things that are generally observed in the North Atlantic and not necessarily all over the world. Okay, so this is the chronology that we obtained from the Tones Valley. And now we're going to go to the Chandra Valley, where several years later, a PhD student, Patricia Eugster, did some work. And there we looked at mostly at ice-polished surfaces. So in contrast to the erratic boulders that we've been looking at in the study that I just presented, here we are now looking more at ice-polished surfaces. Why? Because ice-polished surfaces, such as the one shown here, this is, I think, from the, what is it, the Kunsumla, I guess, right? The pass here from the Chandra into the Spiti Valley. They tell us that the ice has been eroding the surface, and then since it has been receded, there has been no erosion of the surface, right? In contrast to what I mentioned earlier with respect to a pile of sediment, like a moraine, we know that this surface has not eroded since then, because the striations tell us it is still featuring those signatures of glacial abrasion. What we don't know is how thick a snow cover might have existed in the past, or even sediment cover. So there are still uncertainties, but nevertheless, it's an interesting object to study. And so we did that in several places, also including the bedrock ridge I mentioned earlier here in front of the Barashigri Glacier. And in conjunction with dating those surfaces, we also measured striations on them. So these arrows here indicate the flow of ice. And so in this case, the Barashigri, when it was so thick that it was flowing over this bedrock ridge, there was a thick ice stream that extended all the way down to relatively far down the valley. We don't know exactly how far. We have some estimate from reconstructing it, but compared to what it exists today, it's many tens of kilometers farther. Interestingly, also the Samunda Tapu Glacier that was basically the source of this large glacier extending down the Chandra Valley was also flowing over the Kunsumla into the Spiti Valley. And this is shown by these glacial striations that we have here on these, like this one, on these bedrock ridges up there. The ages we obtained are all relatively similar. I mean, there are some outliers like this one, 30,000 years. But in general, we observe that many of the ages were formed during around 20,000 to 15 to 20,000 years. And this suggests us that, which is more closely to the global LGM, that perhaps these areas are already more strongly influenced by the westerlies and more subject to the global temperature control rather than monsoonal precipitation. But this is, I would say, rather speculative. Nevertheless, what we could show is that during 20,000 years ago, there was a huge glacier in this valley, extending many tens of kilometers down and also flowing over into the Spiti Valley. We attempted to reconstruct the size of that glacier using a simple modeling and how the glacier has receded through time, because we also have some ages of 17 to 15,000 years at a little lower elevation in the Chandra Valley. And this is shown by these three cross sections here, A, B, C, where we have samples at different elevations that tell us at what time the glacier must have already covered this site, this particular site that we dated, and when it must have been exposed. And so this way, we were reconstructing the retreat history of this glacier from around 20,000 years, and then 19 to 18, and then 17 to 15,000 years, and then less to 15. So relatively rapid recession of the glacier over a couple of thousand years. Okay, so there was another glacial chronology study, and now I want to take you to the Chota Shigri Glacier, which is one of the sites where one of the glaciers that is monitored through time in order to figure out how it responds to present-day climate change. And so what we did there is that we wanted to get understanding of how fast these kind of features here are eroding. So these steep bedrock hill slopes that are towering above these glaciers, down here is the Chota Chikri Glacier, they are steep, they are little frost and ice and everything. The assumption is that these things must erode fast, I guess, but it's not clear, and we tried to quantify that. How? Well, we didn't go there and collect samples from these bedrock faces because it's just too steep, too cold, too high, too dangerous. So instead, we went to the Chota Chikri Glacier and collected our samples from the medial moraine. Now, the medial moraine is exposing debris that is coming from these kind of source areas up here. So wherever these bedrock surfaces are eroding, the material is falling down onto the glacier surface, and then the glacier is transporting this material first englacially within the ice, and then it brings it to the surface because the glacier is melting on the surface, and then the material is transported on the surface of the ice. And we collected samples from these from this medial moraine. We did some modeling in order to take into account any exposure to cosmic rays during the transport, and then we came up with head wall denudation rates of around 1 to 2 millimeters, considering slope perpendicular, so that these steep slopes are eroding, backwards. If you convert that for 50 to 60 degrees into a vertical denudation rate or a vertical eroding surface, then this would be something between around 1.6 to 4 millimeters per year. So relatively rapid. I just wanted to show, this is a little video. I hope it transmits through the internet well, but it shows how we were modeling the ice flow, including debris that is advected with the ice, in order to be able to interpret our samples, because it gets a little bit more complicated with respect to fluvially transported material. But I don't want to go into the details of this. This is just a little nice video to show. Instead, coming from here now, I want to look into landscape scale denudation rates in the area of the Pavatones in Yamuna Valley. So and this was one of the main topics of my PhD thesis, where the question was really what controls the spatial pattern of denudation in this part of the Himalaya. And in order to answer this question, as mentioned earlier, we went down to the river and collected sediment from the bank or from the river itself, mostly sand sediment, several bags, and then transported that back to the lab in order to isolate quartz minerals, dissolve them, and isolate 10 beryllium or beryllium, and then measure the 10 beryllium concentration. Now, doing that for many different catchments, as can be shown here in these places, we obtained catchment average denudation rates that are shown on the right-hand side. And what we found is that denudation rates are the highest in the high Himalaya. So we obtain rates that are between 1 and several millimeters per year in those upper parts of these catchments. I ought to say that denudation rates that are something like 4 millimeters per year or higher, they are more questionable because the concentrations are very, very low. And so it's not entirely clear whether this is a true denudation rate or it could also be affected by processes such as landsliding and other things that are complicating the interpretation of such data. But the general picture we obtain is that here 0.9, 1.8, 1.4, 1.9 or something is giving us high denudation rates here and then much lower denudation rates here. So 0.16, 1.3, 1.5 and so forth. Those areas here are a little bit eroding a little bit faster, but not dramatically, right? So it's 0.3, 0.3, 0.4. So they are within a similar range of values that is about almost an order of magnitude lower than the rates that we see up here. Now, in the next slide, I want to take those measurements and project them into a swath profile that is draped across the mountain range like this. So perpendicular to the strike of the range. And there we go. And so this way we can look at across strike variations in denudation rate. The x-axis shows you the distance from the mountain front. So this would be the mountain front here, or Dehradun or Chandigarh or something like this. And then at greater distance towards the northeast from the mountain range, at some point we get those samples where we have low denudation rates, and they are all here. So the width of these rectangles depicts the width of the catchments that we sampled, and then the y-axis gives you the denudation rate. And then as we transition from the lesser Himalaya towards the high Himalaya, we get these much higher denudation rates. Some of these catchments have been previously glaciated, so this introduces some sort of uncertainty. But even considering that there has been glaciation, we nevertheless obtain denudation rates that are on average much higher than here. And so the interpretation here is that here's the same swath profile showing you the elevation, so lesser Himalaya and then high Himalaya. And here's the rainfall. So rainfall, as observed by Bodo Bokhagen and Dirk Burbank, is high here at the front, right? This is where the MBT is, and this is the Mohand range, basically. And then it gets a little lower, and then it peaks a little bit in again as we transition into the greater Himalaya or high Himalaya, and then it drops down, because this is mostly rainfall, not snowfall, not precipitation, but rainfall. But the increases in denudation rate occurs where basically we have a decrease in rainfall again. This is the first high precipitation band. This is the second, referring to the map that I showed in the beginning of the talk. But the denudation rates don't really go up and down like the rainfall pattern here. Rather, they stay low and then they increase. And the reason for that is we think has to do with box. And so this figure shows you how we structure of it here. It's based on tomography data from Caldwell et al. This is a data set that was obtained farther to the east in the area of the Alaknanda River. But considering similar geometries of the main Himalayan thrust beneath this area, we would expect that the MHT has a relatively gentle sloping flat portion here, which then turn to a steam here in the area of where you also see the Munziari thrust or the MCT. And it's exactly in this area where we have the ramp that we see the increase in denudation rates, where we also see the increase in topography. And so the idea here is that if you simply take a model where you take, if you consider a model where you simply take an accretionary wedge or orogenic wedge like the Himalaya, and you slide it above this MHT, simply because there is a steep ramp, you induce high uplift rates, such as the ones predicted here in the area of the high Himalaya, whereas because of the gentle slope, the MHT, you induce low uplift rates, such as in the lesser Himalaya. So it seems that simply because of the geometry of the main Himalayan thrust, you are able to explain the spatial pattern of denudation rates in this part of the Himalaya. And this is our favorite interpretation. This interpretation is not too different from other interpretations, such as what Godard et al. Have found in Nepal. And there's also the study by Jérôme Lavey and Jean-Philippe Avouac many years ago, where they looked at patterns of river incision in Nepal. And they also found that where they find where they see the ramp in the MHT associated also here with microseismicity, this is the place where they observe the fastest river incision. And then in the lesser Himalaya here, where the MHT is more gentle sloping, river incision rates go down. When looking at the, for instance, the Yamuna River, this is also the site where we see most of the terraces preserved. Whereas then in the frontal parts, where the MFT or the MBT is located, we're losing again the terraces, presumably because erosion rates, or in this case, river incision rates, are increasing again. Okay, so this brings me to the next one here. This is a study published a little later, again from the same area, but in this case, we are actually looking at those terrace deposits. Here is a photograph from the Yamuna River down here in the area of Lakamandal. So I think this is a temple that is I'm not entirely sure anymore, but I think it's somewhere up here. And this is a tributary coming in, and this terrace deposit here is nicely exposed by the river, by the road that has been cut into the slope of the terrace. And so the river allowed us to access the terrace material, and we collected our samples from the terrace deposit or from the valley fill in various places. We did this not only here in Lakamandal, but also in other places. I like this picture because it nicely shows this a cut terrace that is down here, but also the top valley fill, which can be traced all the way here. And this is a pronounced valley fill that occurs all over the Yamuna River, the Tons River, and the Paba River. And one of the things that we wanted to understand is whether these the valley fill and the aggradation that lies behind it is related to climatic forcing or something else. So the available theories or hypotheses about valley aggradation in the Himalaya can be divided into two categories. One is considering that there is a supply-limited aggradation, or this is phrased it, where people think that during the early Holocene, where we know it has been much wetter, people suggested that there was a pulse of sediment flux coming down from the hill slopes into the river, presumably by landsliding, which then overwhelmed the rivers, which had not enough water to transport all the sediment and caused the aggradation. And then after it has been aggraded, the valleys incised again because the sediment flux went down because the hill slopes were depleted. Water was still high with a lot of monsoon precipitation. And then these valleys, the rivers incised into the valley fill again. So this is one interpretation. The other one would be that it's more related to transport limited aggradation, that we basically have already during the a lot of sediment produced by glaciers, but at the same time relatively low discharge because monsoon precipitation was relatively lower during glacial time. And so in this wall, aggradation occurred over a longer time period during the glacial period, and then during the early Holocene, when water flux was high, so precipitation was high, the valleys incised. In order to test these different models, we went to the field and collected samples both for the valley fills, but also for quantifying denudation rates to see what the sediment fluxes would have been in the. Whoops, there we go. So the first thing around is identify them and also measure them. So we used differential GPS back then in order to trace the top surfaces of these terraces in all these places that are denoted here by the triangles. Concurrently, we collected samples from these places where we see yellow dots. Some of the samples are geology, and some of them are for paleo-erosion rates. I'm not going to go through all the samples in great detail, but because it would take too long, but just summarize the main results. But I want to show this figure here because it nicely shows how these in the Yamuna and the Tons and the Paba, the top surfaces connect well and yield a terrace, a valley fill that can be traced across all of these valleys. And we also use this reconstruction in order to estimate the amount of sediment that is stored in these valleys. Note also that here, where the main boundary thrust is, we don't really have any terraces. So it's not entirely clear what have been connected to the fill in the past. at least in these parts, in the basal layer, erosion rates are much lower. We have beautiful remnants of fluvial terraces. So we collected our samples in such sites. Why? Because we know that because of the road cut, the sample has been shielded from cosmic rays at least by 6 meters of material in the past. And this is important because we don't want that our samples that we measure contain a material or contain 10 beryllium concentrations that is derived from the present exposure. We want the material that has been implanted in these samples back in the past. And therefore, we collected samples only from these shielded road cuts. And when we analyze our samples, we found that during the late Pleistocene, it seems that our erosion rates have been mostly higher compared to our recent erosion rates. So all of these samples here, these are for every sample, we have several points because they reflect different depositional ages, because with our geochronology data, we were not able to constrain the depositional age very precisely. So we took a conservative approach and assumed different depositional ages, including also differences in snow lines and everything, in order to get a sense of what the effect would be on our estimates with these different ages and snowline estimates. But overall, we remain in the field where the late Pleistocene erosion rates have been higher than recent erosion rates, on average by about a factor of 2. That was the conclusion back then, but I was not very satisfied by these results because we had a lot of problems dating them. We had scattered samples all over the place. And so we went back to the field later with a student, one of the first students that I supervised during his PhD. One of the concerns was also, what about glaciers in the past? Because we know that there have been extensive glaciers in the upper parts of these valleys. And it could be that some of the material that we dated was coming from underneath the ice. And this becomes problematic because I mentioned earlier that thick ice cover, like hundreds of meters of ice, is shielding the subsurface bedrock, and no more production occurs. But that might result into sediment that is coming from underneath the ice that has a concentration of 0. And so any glacial sediment would mix with fluvial-derived sediments and lower the concentration that we measure. And we might misinterpret these signatures for increased denudation rate. And therefore, we went back and to do a very systematic study. So there is a beautifully exposed terrace here in the area, in the vicinity of Barkot, in the Yamuna River. And there we collected samples, many samples, all the way from the bottom here where the river is to the top somewhere up there. Here are the samples. We also collected additional samples for age dating using infrared stimulated luminescence, also C14, and also had an exposure age from the top of the terrace surface. And so the results show us first that the terrace was, that the valley fill here was aggraded somewhere between about 30,000 years and 15,000 years at the top, so during glacial times. And second, when we look at our, I need to go back. In order to figure out this, the impact of glaciers, we also conducted an ice flow modeling. So what we wanted to see is if during these times here, there had been glaciers in the headwaters of the Yamuna Valley, what might be the impact? And so what we did is to use a numerical ice flow model, similar to the one I showed you before for the Chota Shigri, and we regrew the glaciers to the extent that we knew they had in the past. And this was mostly informed by the glacial chronology from the Tones Valley, but we extended our modeling domain also into the Yamuna, where glaciers were present mostly in this part. This is actually the area that I was showing previously with a Google Earth image. And so doing this and taking into account the ice cover in the headwaters and their effect on cosmogenic nuclides, we found that we can actually lower the estimated erosion rates from our samples quite a bit. So this is the result, the main result. Here we have no ice cover correction. There we have ice cover corrected data. This is giving you the erosion rate across the thickness of the terrace that we sampled. And then we also looked at different samples. So quartzite pebbles, we know they come from the Lesser Himalaya. It's basically the Rampur quartzite that is present in that area. And they have no change in erosion rate whatsoever. And we know they come from areas that have never been glaciated. So this is our benchmark basically for unglaciated areas. But then we have crystalline pebbles and we have sand. Sand comes from all over the place, from the Lesser Himalaya, from the High Himalaya, and the crystalline pebbles come mostly from the High Himalaya. And without ice cover correction, we get these different patterns of erosion rates. But when we correct for ice cover and its effect on denudation rates, then we see that the crystalline pebbles and the sand, they all move very close to the erosion rate that we obtain also for the quartzite pebbles. So the conclusion from this study is that when we correct for ice cover in our production rates, we find that the unglaciated areas had similar denudation rates as today, whereas the glaciated areas are likely still a little bit higher denudation rates, but it's really difficult to quantify that due to the unknown quantity of subglacial derived sediment. So you can see it's already getting a little bit more complicated. And I'm going to end this now with the last study, which is in preparation. These are also still samples I collected during my PhD and which have been sitting around for many, many years. And then finally, we managed to analyze the samples. And I'm lagging behind in wrapping up that paper. But it's data that is coming from the Spiti Valley. And the reason is we are interested in this area is because it's kind of it's in an arid area that sits in between these really arid areas in the north and the much wetter areas in the south. But it also seems to be in a transitional phase because we know that the Zada Basin here in the upper part of the Sutlej River has been accumulating sediments between about 9 to 1 million years ago. But then since about 1 million years ago, it got reintegrated with the Sutlej and is now incising. So the discharge that goes through the Zada Basin has been increasing, which means the Sutlej River has much greater incisive power, which should also affect the landscape evolution here in those areas in the upper Spiti Valley. And so we went there and collected samples from low relief, high elevation, low relief surfaces that can be found here. Casa is somewhere down there, and then some of you may know these relatively low relief areas up there. And then we also collected samples from bedrock terraces in this little tributary in order to constrain the incision rate of that river. Again, this is work in progress, and I don't want to go into all the details. This feature here, these low relief surfaces, are a little bit abnormal in the sense that they stand visually in the landscape, but they also coincide with a syncline and with a certain unit that is exposed here. Luckily, this unit is also quartz containing, although it contains a lot of carbonate also, and so we could use 10 beryllium to quantify denudation rates. These ages here are exposure ages of the terraces that we dated in this canyon. They tell us something about the incision history. Here are some impressions from the field. So this is high up on these low relief surfaces, similar there. Even there on these low relief surfaces, we see deposits. So we took also a sample from this from the surface here. These are pebbles, but they are really glued together by carbonates in the headwaters. And this is showing that is incising, and there are some of these surfaces are here that allowed us to date the incision. Interestingly, here sordid stripes tell us that there's a periglacial disease acting and transporting sediment. Now, what we obtained are erosion rates that are pretty low. So there are a few ones that stand out high, but most of them are really low, and they are on the order of, let's say, 10 millimeter per kilo year or something like this. when using those exposure ages from these terraces here, we can, these are the ages, these are the height above the river, you can fit the data with a curve that goes through the origin, and that tells you something about the incision rate of the river, and which is on the order of 5 meters per kiloyears. These ones here tell us that denudation has been mostly less than 0.05 meters per kiloyear, so 2 orders of magnitude lower than the incision of the river. And we interpret these two data sets basically to highlight that incision of these low relief, high elevation, low relief surfaces has occurred very relatively rapidly during the last glacial period, and is creating this abnormal feature that we can currently observe in this area. When we compare our data with other published data sets from the area, we see that here in the north, in the Shiok Valley, in the Ladakh area, denudation rates are on the order of 10 to 100 meters per million year or millimeter per kiloyear, and similar to the low denudation rates we obtain from this high elevation, low relief surface. But then as we go farther to the south in the Sutlej and in the Garhwal Himalaya area, we see the denudation rates go up 2 orders of magnitude to about 1 millimeter per year or 1,000 meters per million years. And so we think that this, similar to the incision rate of the river into this low relief surface. And so we think that what we're observing is really a transient response of the landscape, as the Sutlej is now incising headwards into the Zada Basin, but also into the Spiti, and is accelerating incision in these areas here. Okay, so this was what I wanted to say. In conclusion, I hope I could show that cosmogenic nuclides are pretty versatile tools to quantify the history and evolution of the Earth's surface, and that in the Northwestern Himalaya, we observed denudation rates that are very high in the High Himalaya, intermediate in the Lesser Himalaya, and very low in the Tethyan Himalaya. The spatial pattern in denudation reflects first-order tectonic controls, which is modulated by climatic patterns through time. The impact or the quaternary climatic changes caused glacier advances and retreat, some related to monsoonal variations, some probably more related to temperature variations globally, which had significant impact on landscapes. The same applies to their recent retreat, which I didn't cover, but I wanted to mention. And the unglaciated regions show only minor temporal variations in the denudation rates that we quantify with cosmogenic nuclides, but strong variations in river discharge presumably are the cause for the aggradation and incision and the beautiful fill terraces that we see present in these areas nowadays. The Spiti region appears to undergo significant geomorphic changes since quaternary times, so since about 1 million years at least, which is probably expected to continue to some extent, although it remains dry and arid up there, so it will never evolve into something that we see on the southern slope of the Himalaya. And with this, I would like to thank you for your attention.
Thank you, Professor, for such a nice, informative session. Now I'll open the house for questions. I guess Uday Sharma is trying to ask something. Over to you, Uday.
Yeah, just a moment. Thank you so much for such a wonderful lecture, Dirk. And I am also really thankful to Shubham sir also for bringing you here on this platform, and we could discuss this wonderful research. So I have
Thank
been
you.
personally also working in Spiti Valley, more or less in the similar lines, trying to find the deglaciation extents within Spiti. So I
Oh,
saw the data you were showing from Chicham area. Can you just go on that slide?
okay.
Just in the last couple of slides you were showing.
Sure. Let me go back to the presentation. Which
Yeah.
one?
Yeah, this one is all right. So I just wanted to know what are these red dots and green dots showcasing? Are
Yeah,
these different types of chronologies or something else?
yeah. So the green dots, they are past, but has then been incising further. And the ages tell us something about the incision rate of that river, shown here in this slide.
So have you found any signatures of the glaciations in this particular area in the past or something like that, which have driven this incision also?
Yeah, not really. To me, it's really difficult to find. So there, I haven't seen any moraines or anything within the Spiti Valley here. I mean, you probably know that there are some flake deposits farther down here.
Yeah. In Mane. Just before Mane.
Yeah, there are beautiful moraines in the Pin Valley. And as I said, higher up, there are some moraines that relate. So that it was coming over from the Chandra Valley, as also shown by glacial striations in the direction and so on. But I haven't seen any convincing moraines or anything in the Spiti Valley. However, I mean, there has been a strong overprint by fluvial processes. So it's not, if it could be that glacier has been advancing quite far, but I wouldn't say probably not during more recent times, like not during LGM or something like this. Yeah. Sure.
What could be the reason that glaciation has not exceeded in particular towards the Spiti, whereas it has a quite long extent towards the Chandra? What could be the reason it's not that developed in Spiti in the past?
Yeah, I think to me at least, sorry, I'm going back to the Chandra thing.
Yeah.
So even nowadays, you can see that the Samunda Tapu Glacier is pretty big. The Barashigri is pretty big. So you have a lot of glaciation in these places here, which is in part related to the topography, which is pretty high. But it's also, in my opinion, related to precipitation that is transported in this area from the westerlies or with the westerlies. I think there has been, together with a colleague, we had been studying rain gauge data and discharge data from this entire area, which really shows that there is more wintertime precipitation in this area compared to in the Sutlej area. So this wintertime precipitation derived from the westerlies is a good source of growing glaciers, and we see that these glaciers have been big. I could imagine that as you then transition over to the Spiti here, the mountains are not as high anymore as they are here. You don't currently have that big glaciers, so the potential to grow big glaciers is lower. Plus, if you rain out or if precipitation occurs here, then you have less precipitation as you go farther to the east, at least with respect to the westerlies. And that could result in less big glaciers in the upper Spiti Valley.
Okay, thank you so much. I don't know. I have many questions, and I think others might be waiting. But just the last question I want to ask. So, if you're saying that this topographic prominence, which is more prominent in Chandra compared to Spiti, which has comparatively low elevation in compared to Chandra, so in the past, when during the LGM or even during the younger dryas, wasn't that in that time there was a case that glaciations might have extended quite below towards Kaza and all that those places also, because we see those big wide U-shaped valleys which are typical character of glaciations. So isn't there a possibility to study that?
Yeah, I mean, as I said, I could imagine that during even longer times ago, glaciers have been advancing quite far down. But during the last glacial cycle, I don't think so. For the reason that we see terraces there, and my colleague Bodo Bokhagen, I've seen once, he presented, I think, at an AGU
poster. Even I saw that presentation online somewhere.
Yeah, and I think he has some exposure ages that are something like 100,000 years ago. So, and I don't expect these terraces to survive if there is a big glacier that is plowing through the Spiti Valley that you can retain these valley fills as they are today. If there was one, then I would expect a big moraine or something like this, which we don't see, right? So for that reason, I don't think that it occurred during the last glacial cycle. Any really big advance. There might be something smaller, so something peeking into this area maybe, but it would not have had a big effect on the landscape there. And the U-shaped valleys are usually you can say they are interesting signatures, but you have to be careful with them. And for two reasons. First of all, you can create similar features by simply, if you have a V-shaped valley and you fill it up with sediment, then it is a box-shaped valley. And if you then have a little bit of talus deposits on the base, you create a U-shaped valley, which has nothing to do with a glacial valley. It's simply because you're elevating the valley floor because of aggregating, of depositing sediments there. So, and especially true in arid landscapes where you quickly get very steep slopes. And so this area above Casa where you have these relatively flat-lying or gently dipping sedimentary strata of the Tethyan series, and they form very steep slopes. And so wherever you have these steep slopes, you already have a steep slope, like you would expect after glaciation in a U-shaped valley. And then at the foot, you have talus deposits. And again, you create something that is U-shaped, but has nothing necessarily to do with glaciation. So just based on the morphology and U-shape, I would not necessarily trust that this is due to glaciation. But again, take this with a grain of salt, because in the past, who knows, maybe 200,000 years ago, 300,000 years ago, because we see that the landscape up there is evolving so slowly, it is quite likely or possible that you have things occurring in the distant past, which has shaped these areas glacially. We see similar features like this in Ladakh area, where you see, I think Lewis Owen has dated some glacial till to something like 600,000 years ago, which is still present in some places.
Thank you so much for this wonderful lecture. And
sure, and
thank
also
you,
if you have
sir, for
questions
organizing.
or something, don't hesitate. You can always send an
Yeah, I
email.
can all. Sure, sir. Thank you so much.
Sure.
So I would like to invite any other question, if we have any other question from the audience.
Yes, sir.
Yeah, please.
The denudation rate for the glaciated and non-glaciated terrains, is there is any relationship, sir?
I mean, generally, I think that our data, at least from the Gawal area, shows us that it is easy to, or simpler to explain the data based on tectonic processes. So, as I said, with the MHT, where it has a gentle slope, you're basically just moving the Himalaya over a flat part of a thrust fault, and this does not induce a lot of uplift. And it doesn't matter whether you have like rivers or glaciers incising the topography. It's really the uplift is controlled by the MHT. And where you have a steep slope, then you have high uplift rates. And if you have high uplift rates, topography in general tends to attain a shape such that the erosion rate is matching the uplift rate. In the long term, this is a powerful concept to keep in mind, that if tectonics results in growth of topography, the topography grow as long as until the surface processes, and no matter what what processes, whether rivers or glaciers, are matching the uplift rate in the long term. In the short term, this can vary, but in the long term, this will happen. And this is what we call the steady state topography and the steady state in processes. So coming back to your question, whether there is a relation, not necessarily in between fluvial and glacial denudation rates, but they are both linked to tectonic processes. This is the way I would put it.
Okay, sir. Thank you.
Any other
Sure.
question from the audience?
Sorry if it took a little long with the
No, no, sir,
presentation.
we are really enjoying your talk, sir.
Okay, thanks.
Just, I have one question, sir. Like you, I have one or two, three questions. First one is,
Sure.
you said the slope of MHT is very much important. I'm also trying to work in the area near area in the Satluj, basically in the Satluj basin. We cross Rampur, we cross
Mhm.
Munseri Thrust towards the MCT. And right now, what I don't know, this is just assumption. What I'm observing, the most of the landslides, most of the destruction by the rainfall is occurring in that particular area from that Rampur to, I can say, towards the MCT, that is Karcham area in the Kinnaur region. As you were
Yeah.
saying, there was a high uplift is happening in that area, and we are also observing the lots of presence of hot springs in those areas. Specifically in those areas, there are a lot of hot springs in basically present in the Satluj, nearby the Satluj
Mhm.
river. So can we say that this kind of uplift is so much high and it is so much powerful that it is causing landslides and driving all those processes together?
I think yes. I mean, you know yourself that the area you described is located also in the Largi Kulu Rampur
Yeah,
window, tectonic window.
yeah.
And a tectonic window in itself is already an expression of a localized feature. And the river has incised locally, and the Lesser Himalayan, the crystalline series of the Lesser Himalaya, and what is it there? The Munziari thrust is showing you that that we have these this lesser Himalayan imbricates in this area, and I think the which is probably also in line with much of recent research, that the underplating or the basal accretion of the lesser Himalaya is causing this duplex to grow and to cause extraordinarily high uplift rates in that area. And it coincides basically with a high Himalaya, right? Only that the river has incised such a deep valley so that you still get high mountains even higher up along the river. But when looking at thermochronology data, you see that the youngest ages are all located somewhere between Rampur and yeah, where the Baspa Valley is going off or the MCT basically. And then the ages get much older as you go farther to the north. The hot springs are interesting. I don't know exactly how to explain this, but one has to infer that there is higher circulation of hot fluids, obviously. They may also have an impact actually on thermochronology data, which is a little bit of a bummer. But with high uplift rates, yeah, you would have fast incision. High uplift creates oversteepened slopes. Oversteepened slopes are prone to landsliding and things like this. So I think it's all related. You may know or remember the publication. I forgot the author's name, but it's from the Tsangpo gorge, where it's a Nature Geoscience paper, I think, where they mapped landslides from satellite imagery. And Larsen, it's Larsen et al. I don't know what the year was, but they also found that in the Tsangpo Gorge, where you have the highest uplift rates and the highest denudation rates and everything centered in one part, they also observed the highest occurrence of landsliding in that area. So I think it's all related. Yes.
Okay, okay. Now my second question is that these denudation rates are dependent on the normal faults that are still developing in these northwestern Himalayas. One of the prime example is this your Korichango normal fault system, and another one was, it is not that much elaborated. Another one near the MCT is Karcham normal fault, which has created
Mm-hmm.
a high amount of lake sediments in the Baspa River, called a place called Sangla, where we have a lot of the lake deposits are present in that place. So can these normal faults, which are still more active than other fault systems in that area, can impact these denudation rates and everything related to it?
Mm-hmm. Yeah, two aspects maybe. First of all, any fault that creates relief
Yeah.
will induce erosion, right? So it doesn't matter if it's a thrust fault or reverse fault or a normal fault. If you're creating relief, then there will be erosion. And the faster you create the relief in the long term, the faster the erosion rate will be, provided there is enough precipitation for erosion to occur and everything. But so yes, even with the normal fault systems that you addressed, you would expect that it would increase denudation rates, increase erosion rates. I would say up in the north, it's also evident that the Leopargal dome is a horst. It is rising. You have incision and you have activity of normal faults at least farther to the north, and where the earthquake has been. I'm not so sure about the Karcham normal fault and whether it's responsible for the lake damming in the Baspa. I always thought that near Sangla you have this big landslide that might have been responsible for the damming there. And we also know that in the Baspa higher up, there have been significant glaciations. So again, it could be that in the Baspa you have sort of glaciers shaping the topography in the past at some point, which then creates also the space to store sediments there. But I'm not so familiar with the normal fault in those areas there.
Okay, fine. My last question, that is, this technique can be, or this methodology can be used in the lake sediments that is present all over that region, or is it just limited to this fluvial and glacier part?
Yeah, it's the problem is with or the limitation with in situ produced 10 beryllium and quartz is that we need a certain grain size. And this is because on all our quartz grains, we not only have inside of them the in situ produced, so within the mineral lattice, but we also have meteoric 10 beryllium that is produced in the atmosphere at a rate 1,000 times higher. So all this meteoric beryllium is sticking on the surface of the grains. So what we do is we use hydrofluoric acid in order to leach and etch, leach away everything that is around those grains. So once we get to a grain size that is smaller than 100 microns or something, so 0.1 millimeter, then typically what happens is that we are leaching away the material. And so grain lake sediments with fine grain sizes that are silt-sized or something like this cannot be used. There are approaches, also something that my colleague here at GFZ is using. She's using meteoric 10 beryllium, and for those it's possible to go for small grain sizes, silt or even clay-sized grains. But it's more, let's say, still in a development stage, this approach, and it has much greater uncertainties relative to in situ produced 10 beryllium.
Okay, fine. So there is one question from Mr. Sarabjit Singh in he's saying, in the literature there seems to be an ambiguity about the basin size for measuring erosion rate from the cosmogenics. How do you think the basin size impact erosion rates? Are there some standard for determination of the basin size?
Yeah. So in general, you could say, I mean, this is in general, when you say you take a bag of sand from a river and measure the concentration in order to infer denudation rate, you make a lot of assumptions first. Based on these assumptions, you set up an equation that you then use in order to convert the measured concentration into a denudation rate estimate. So it's a relatively long path, and it's not like measuring the size of a tree, right? Measuring the size of a tree does not have a lot of assumptions. But in this case, you make a lot of assumptions. And there are a lot of ways to violate these assumptions, and this is where the problems arise. And so when a catchment is eroding by landslides, predominantly, like you said, in the Sutlej, for instance, then it could be that the sample that you collected is not an average of grains coming from all over the catchment, but it could be that your grains are coming just from this recent landslide. And this would be a problem, because then you make assumptions that are violated by this landslide in your sample. But there have been studies, and I think one of the first studies was by Nimi and others, and then there are later ones by Ioannidis and others, where people looked at, okay, so what happens in a place like the Himalaya, where landsliding may occur frequently and is important and so on, when we collect samples for cosmogenic nuclides. Again, these studies employ numerical models, and they also make assumptions, so it's not free of assumptions. But both of them converge in a way that they say, even if landsliding is an important process, if you go to a catchment that is large enough, and large enough typically refers to something like 10 square kilometers in size, then even then you get still reasonable results with cosmogenic nuclides. Whereas if you go to smaller catchments, then it could be that you sample a landslide, or you sample material that does not come from a landslide and gives you too low an estimate of an erosion rate. So you could be too low or too high, depending on the recent occurrence of a landslide or the non-occurrence of a landslide. But if you go to a large enough catchment, then it seems to be averaging out.
Okay, thank you, Professor. And one last request. Can you please share some kind of message to my undergrad students, how they can shape and mold their career in the geosciences? As you know, we live in the Northwestern Himalayas, but these kind of techniques are far more accessible to us. They are very limited access for us, people like us. What kind of message you want to give to our students, so they can be motivated and they can feel and they can pursue geosciences in a research on or in other fields?
Okay, wow. That's a tricky one. I mean, but I like it. The examples I've been showing here are using certain tools, cosmogenic nuclides, and it's clear that these tools are not available everywhere, and they require certain labs that are also not available everywhere. For instance, my colleague Sanjay Kumar Mandal in Kolkata, he has now set up a lab in order to extract beryllium out of samples or even aluminum. And so he would be a natural collaborator in India in order to employ such methods. But it's clear that it requires A, a lot of time, and B, also some funds in order to pay for the AMS measurements. This is something that is always a bit of a limiting factor when applying those techniques. Now, when thinking about students at your college, I would say it's not crucial, it's not important to use cosmogenic nuclides. What is more important, I think, is to really be fascinated by the earth sciences, be fascinated by understanding how the earth works, and also be maybe motivated to help influence and shape the earth sciences of the future, especially with consideration the huge problems that lie ahead of us. So climate change is just one of them, but the energy transition we try to achieve in many countries requires new approaches of finding resources and sustainable use of resources. The pressure on land and land use by humans on landscapes is increasing with time, and there are so many open questions available for geoscience students that it does not require cosmogenic nuclides. What it requires is really a motivation, a strong motivation to be active in this field, and curiosity about understanding how the Earth works. And if this is something that you are equipped with, then I think you can pursue in many different directions, whether it is associated to geology, geomorphology, or even geophysics, or remote sensing, or whatever, where you can contribute a lot and you really delve in this field, in this fascinating field of geosciences with all its opportunities. Some people may be more inclined towards field work, some might like further the lab work, or even computer and modeling work. But everything is valuable, and just nourish the passion that you have, and go out and observe the nature, and this is what I would say is the most important thing.
Okay, thank you, Professor, for such a nice motivational words. And so we'll be moving to the end of the session. So
Hmm.
I'm very grateful to you, Professor, and to all the participants who have joined with us in this program. And again, I'm very grateful, I'm very thankful, and we'll be sending you more emails further so that we can be doing some kind of program like this again. And
Sure.
again, Professor, I'm very thankful and grateful to you. Thank you very much, sir.
Yeah, I thank you for the invitation. It has been great, and I hope that I can come by and visit you in Shimla when
Yeah.
I will be there next time. I don't know when it will happen, but I'm sure it's going to happen, and then I will at some point I will notify you in advance, but then knock on your door.
Okay. Sure, Professor. Sure. Thank you.
Okay. Well, I thank you, and have a good rest of the day.
Sorry, pardon, Professor.
Oh, sorry, I was just saying thank you again, and I wish you a great day, all of you.
Thank you, Professor. Goodbye.
Bye.
Bye.